So in particular, starting this week, actually, Ramesh started to hold his group meetings on Monday. Is it at 1:30? And then at 11 there is the philosophy.
Yesterday was 11, but start regularly will be 3:30 moving forward.
3:30. Okay, so 1:30 is Ramesh on Mondays, and 3:30 Eric on philosophy related to black holes and space-times and so forth. That's on Monday. Then Tuesday we have our forum here at 1 to 2:30. We hope to do something also on Fridays. Shep Dolman holds often a group meeting and will potentially hold it here. And so there will be events almost every day throughout the week. We are still in the process of establishing the framework, but at any event, Bill will send out an announcement on the weekly calendar every week. And there are also talks related to black holes and gravitational waves at the Center for Astrophysics that Bill will include in the weekly announcement. So just stay tuned, because you could just monitor the events that you want to attend in advance. He will send it either on Friday or on Monday. That's all. So we can start the program.
So hi everyone, it's a great pleasure to introduce our first speaker today, Jonathan Luke, who's visiting us from Stanford University, where he is an assistant professor. So Dr. Luke obtained his PhD from Princeton and then traveled to quite a few places, including University of Pennsylvania, MIT, and Cambridge University, before going to Stanford. He's done a lot of work on black hole space-time, studying perturbations and gravitational waves in these. And today he has some exciting things to tell us about the cosmic conjecture, which we already have had a discussion about last semester at the beach. So,
thank you very much. Thank you very much for the introduction and also for the kind invitation. Needless to say, it's my first time here, and also needless to say, it's a great honor to be here. So my point of view, sort of my training for this subject is from mathematics, but I would try to give a talk that sort of hopefully is sufficiently general, but feel free to interrupt me at any time. So I'd like to begin sort of, well, this talk is about the strong cosmic censorship conjecture. Of course, this is a conjecture in classical general relativity. So let me begin there. Not that because I think I need to tell you what relativity is, but there's a certain sort of point of view I would like to emphasize. So of course, we all know what general relativity is about. So this is about the study of 3 + 1 dimensional Lorentzian manifolds. So in particular, the metric for this manifold has to satisfy Einstein's equation. For now, I will not tell you what the matter field or what T mu is, and I'll sort of introduce different matter models as we need. And we were, of course, most interested in the case of vacuum, where the equation just reduces to which equals 0. So the way I want to think about general relativity, or more precisely the Einstein's equation, is from a dynamical point of view. So I will sort of always think from the point of view of this theorem, a celebrated 1969 result of Shokibara and Gersh. What it says is that, well, you can think of Einstein's equation as a dynamical equation. You can give initial data, and initial data consists of, well, telling you what sort of things are happening now. So a 3-dimensional Riemannian manifold, well, with a Riemannian metric and also a symmetric 2-tensor, well, you should think of as what will be the first and second fundamental form of the embedding of this 3-manifold in your space-time. And of course, okay, as we all know, they have to satisfy some constraints equations, and once you have this, then the theorem tells you that you can solve, you can think of this dynamically, you know what happens now. Then there's a unique maximal globally hyperbolic development, well, let's again call it MG, where sort of our prescribed data is indeed the data, and where the solution actually solves, let's say, the Einstein vacuum equations. Of course, well, already here, you see that, well, we have constraints equation. Already, constraints give you a lot of non-trivial information. And of course, there's the celebrated positive mass theorem proven by Shane and Yao. And in this formulation, I would also like to add that, well, you can also add matter field in this formulation if you put appropriate also initial data for matter, and then you can again have initial value problem for Einstein consistent matter. And once we have this sort of setting of initial value problem, then I would like to consider problems that we think of for evolution equations in mathematics, we can ask about questions of stability, ask about questions of genericity from the point of view of sort of generic initial data, what happened to the solution. Okay. So now I would like to introduce what the strong cosmic censorship conjecture is, but to do this, it's useful to review some of the very classical solutions in general relativity. So first, of course, there's the Schwarzschild solution that we all know and love. So, since I tell you I always want to think about general relativity from the initial value data point of view, so immediately I want to consider the maximal Schwarzschild, which I want to think of as the maximal globally hyperbolic development of Schwarzschild data. And there is a manifold of R2 cross S2, and the local coordinate, you can write it down, and okay, you have to do something to sort of go between coordinate patches. But as is well known, sort of Schwarzschild has the property that it has a black hole region, and in the black hole region, sort of something singular happens. One way to capture this is that, the Crutchman scalar, which is curvature invariant, actually blows up inside the black hole. And one thing you can say is that, it is an actual singularity in a sense because, this is something that has to do with the curvature, it's not depending on the coordinate system. You cannot extend the maximal Schwarzschild, you cannot extend this maximal globally hyperbolic development to any bigger space-time with the Lorentzian manifold that's C2. So it has continuous second derivative. Right? So this is obstructed to that. But what sort of is harder is that actually something much worse happens in Schwarzschild. In fact, you cannot extend the metric continuously. And somehow this is actually only known very recently, a result of Spinsky. And what you should think, sort of, if you sort of come from more physical background, you should think this is sort of a mathematical way of saying the statement that you want to say that Schwarzschild is very bad in the sense that you have infinite tidal definitions.
But what are all these extensions? They're all solutions.
Now, so now at this point I don't even care about whether extensions are solutions. I'm saying that it's not possible to have any extension with continuous metric. Okay, so in particular, certainly there would be no extension as solutions. Because, if I want to talk about solutions, at least all the notions we at least need the metric to be continuous. So the statement is no extension as continuous. So, this is a Penrose diagram, and of course there is a. Sorry, I missed.
I mean, when you read textbooks, there are all these extensions, right?
Of Schwarzschild.
Yeah, but he's talking about it going through the singularity.
Yeah, but
there aren't extensions like that.
Oh, I see. That's so different. Okay.
Yeah, I mean, you can also say.
Type solutions.
Oh no, sorry. So again, okay. So maybe that's the confusion. So
Yes,
what I think about is I always think sort of from the point of view of Schoenberg and Garish. I think of Schwarzschild. So when I talk about Schwarzschild, I really talk about sort of Schwarzschild as development of a complete initial data. Okay. So usually when you talk about extension, you think of this region of the exterior. You can extend, you can go inside the black hole. But for me, sort of the whole thing, the maximal thing, is my Schwarzschild, and this you cannot extend for. And this,
okay.
right. So in the horizon, of course,
Thank you.
we all know that nothing serious actually happens.
Right.
But in contrast to the horizon, something actually serious happens here. So that's what the picture is supposed to say. So now, of course, the story is very different from the story in Kerr. So we know very well Schwarzschild is a one-parameter subfamily of a two-parameter family of solutions. Kerr, what's important about Kerr is that now I want to again think of Kerr. Of course, you can talk about maximal analytic extension of Kerr, but that's not how I want to think about Kerr. Because I always want to think of general relativity as sort of dynamical theory, so I want to think of just the maximal globally hyperbolic development of Kerr initial data. Okay? So if you want a picture, this is the picture. So I have complete two-ended data, and this is the maximal globally hyperbolic development. Okay? So again, if you just look at the exterior, you can extend inside, there's a black hole region. And what's very different from Schwarzschild is, of course, it has no singularity here. I mean, if you extend analytically, there's some singularity somewhere, but that's not part of my space-time. I only think about what's determined by data. This is the maximal globally hyperbolic development. And it ends completely smoothly. Yes, in contrast to Schwarzschild. So then, what happens is that, in fact, you can extend your space-time through what's known as the Cauchy horizon, the horizon for the Cauchy problem. And what's sort of more troubling is not only that you can extend, and well, you can extend smoothly because everything is smooth, and moreover, you can actually convince yourself that well, you can extend. For instance, you can find a hypersurface. Post initial data on this hypersurface. Use the theorem of Joao and Kerr, and then your extension. You have a little bit of extension, and that extension is also a solution to the Einstein's equation. But now this is quite troubling because, of course, you post initial data, you have a choice of initial data, so you have non-equivalent ways of extending. In particular,
that's not surprising, right? I mean, that's because there's this time-length singularity or whatever, and you can imagine putting new boundary conditions there. I mean, it's like in anti-de Sitter space, if there's a time-length boundary.
so it's different because okay, anti-de Sitter, to begin with, it's not globally hyperbolic.
Yeah.
So, but now I'm looking at the difference is, of course, here I look at asymptotically flat initial data, which is complete. And what happens is this is something that happens dynamically. I form a Cauchy horizon, which has this property.
I mean, you can in anti-de Sitter, you could also take the domain of dependence of some time slice. And then
Right. In anti-de Sitter, you also have this. Right.
So
But
the same kind of picture.
right. But the one that's interested sort of from the asymptotically flat case, then we know examples which are not like that, right? Minkowski is not like that.
Okay.
This feels strange. Of course, if you look at a piece of Minkowski, it would be like that. But I mean, this is something I'm interested in because of asymptotic flat.
But you used the word troubling. What's troubling about
Right,
it?
exactly.
Right. Okay. Yeah. Okay. It's troubling to me, let's say.
Why are you troubled?
But in the sense that, well, in the following sense, right? In the following sense of the closure of the theorem, right? I want to consider sort of asymptotically flat data. I want to say, well, Joao and Kerr tells me that there is a maximal globally hyperbolic development. I want to say somehow there's determinism in the sense of this maximal global hyperbolic development is actually maximal, in the sense that I cannot extend it further as a solution. So this, I would hope to have sort of a closure of the theory. And somehow if Kerr is here, then this. I mean, what I want to say is that doesn't happen.
But why do you hope there's a closure? Or why? I mean, why would you hope that? I mean,
You just don't want to. He doesn't want to have to impose boundary conditions on the
Well,
time-length
it's,
singularity up there or whatever, right?
Well, okay, it's also in particular.
there's some physical principle that
Yeah,
tell
but
you
it's
you should
also
be able to
it's
do
also
that.
in particular sometimes true, right? That's why. But I'll tell you sort of. It's not only that I hope that, and that's how I'm motivated, but it's also sometimes actually true.
But I mean, achronal slices are not particularly natural things in general relativity if you think of it four-dimensionally. I mean, why worry about all of space at a given moment of time is just not it's not a very relativistic notion. Why care about whether that?
Well, okay, well,
why
it's,
would care about
right.
that thing?
So a particular choice of Cauchy hypersurface. Of course, it's not. I mean, there's no sort of distinguished Cauchy hypersurface that you should think about. But of course, the point of view one takes is that you would be talking about. Well, you can take any Cauchy hypersurface, right? Complete 200 asymptotically flat, and well, they will give you the same maximal globally hyperbolic development. Right? So I mean, I want to think from the point of view of initial value problem, but there's nothing special about the initial hypersurface that I choose. Yes.
The Cauchy horizon is unstable to perturbations, right? So does it matter how you can extend it if you then want to perturb it?
Yeah. So right. So right. Exactly. So I'm going to. So the question that then you would like to understand. I mean, if you sort of take this point of view, that I don't really want this Cauchy horizon, is the question whether the Cauchy horizon is stable. And this is the content of what I'm going to tell you.
So you're saying that there are extensions which make it stable?
Okay. So, I mean, okay, one would think, okay, so let me quickly say sort of what I want to be true. So the Jonas censorship conjecture sort of formulated in this language is that I want to say that, well, one way to say that is that, well, what you see in Kerr is not stable. You don't expect that in general. Well, you can be more ambitious and say that, well, even actually in the generic case, Kerr is very, very special. And if you look at generic asymptotic data, then what happened in Kerr doesn't happen. So it's future inextendable as a suitably regular Lorentzian manifold. Okay, so that that would be consistent with the expectation that the smooth Cauchy horizon of Kerr is unstable. So you perturb, something wrong happens, as was suggested. So then, of course, even if you have this picture, you would ask the question of sort of what is that bad thing that happens. Right? So okay, so one way you can say it, for instance, is maybe the bad thing that happens is that sort of a Schwarzschild bad. So you can formulate it in the language that we talk about Schwarzschild. You can say that, well, maybe if maximal global future development to generic data, actually you can extend with C0. This would also be consistent with the expectation that tidal deformations are infinite. So, well, okay, so we may all expect something like this to be true, instability of Cauchy horizon. Turns out already it's understood, well, okay, sorry, one more thing I want to say. So, okay, so I would eventually want to say something about Kerr, but let's say for the next 5 minutes, let me not get to Kerr yet, because Kerr is too complicated, so I want to put myself still in the strictly symmetric world. So let's think about Reissner Nordstr, which of course has the property that is strictly symmetric, has this metric, and has the same Penrose diagram as Kerr. Okay, so now you want to study sort of what happens to the Cauchy horizon, let's say even when you put Reissner Nordstr. So it turns out what happens is much more subtle than just saying whether something is stable or unstable, and in fact this has already been understood quite early on in the physics literature, with many people having worked on this. But in the celebrated work of Poisson and Israel, what they suggested is that the following should happen. I mean, they were looking at some heuristics for the Einstein-Dust model in spherical symmetry. What they suggest is that you should see both stability and instability properties. So in particular, well, you can perturb your data, let's say. I would still want to think of this point of view of initial value problem. Then what happens is that, well, first you will still have a Cauchy horizon. So that is to say, if you look at perturbation of, let's say, Reissner Nordstr, it's not that the Cauchy horizon is so unstable that it will go away. It will still be there. You will still have an L Cauchy horizon. But on the other hand, and in particular, you also expect the metric coefficients to remain continuous. That sort of is what they say. But then what they suggest, well, there is instability happening, and that instability is at the Hawking-Marshall blow. So this is what they call mass inflation scenario. Okay, so this is in particular in contrast to some of the earlier suggestions that maybe the metric coefficient will also break down. We don't have C0 extension, that you have like a Schwarzschild behavior. So what Poisson and Israel suggested is that it's slightly more subtle. Everything is still C0, but then it's a mass that blows up. Okay?
So how do you say that the metric coefficients are continuous in a gauge invariant way?
So there's no such way. So the statement is that there exists a coordinate system that just happens. Or alternatively, in the way sort of formulated previously, is that there exists an extension such that the metric remains continuous. Okay, so I mean, if I say it like that, then it's geometry theory. Okay, very good. So now I want to actually study this in spherical symmetry. I want to sort of have a setting which analytically is still sort of simple, so I want to consider this model. And in fact, this was carried out maybe around 18 years ago in the thesis of deformed. So the problem was, I want to be in spherical symmetry. I want to see Reissner Nordstr, so I better add in Maxwell. But I don't want to see a Birkhoff theorem, so I better also add in a scalar field. So then this is a system I consider. The coupling is only very weak, sort of the scalar field and the Maxwell field couple only through the geometry. In particular, here sort of you can easily show that the Maxwell field is actually only depends on the constant, which is the charge. Okay. So now you want to ask questions that within this model in spherical symmetry. What do you know about stability and instability of the Reissner Nordstr Cauchy horizon? Or more ambitiously, what can you say about sort of general large data solutions, which are not close to anything? So, well, the first thing you say is the result of Christodoulou, which says, okay, it's still what you hope to be true. The C0 formulation of strong cosmic censorship that generically you cannot extend in with continuous metric is true. Of course, one has to be careful. It's only true, okay, again, within the class of strictly symmetric space-times. if you impose the condition that the charge is 0. Okay? So the result is if you impose the charge as 0, then in fact any data that you consider, the solution is C0 future inextendable. But of course you say, well, this is cheating because you're not even considering Reissner Nordstr, which sort of, at least from the point of view of this talk, is the motivation of this problem. Okay? So you want to understand the case where the charge is not 0. And it turns out, as long as the charge is not 0, the solution is actually always continuously extendable. So that's a result of determinism and determinism. So what they say is exactly what I said there, except I should maybe have one fewer comma. That as long as the charge is not 0, you can always continuously extend. So if you think of charge not being 0 as a generic condition, which of course it's more generic for the charge to be non-zero than 0, then what you can say is that the 0-0 formulation of control-mapping censorship is actually false for this model. Okay? In particular, what they also show is that the boundary of spacetime always have a portion of the Cauchy horizon. So this has nothing to do, you don't have to be close to Reissner Nordstr. As long as you have charge not equal to 0, you must have some Cauchy horizon. So pictorially it's this. So what they can prove actually is you are in one of these two scenarios. Either you completely like Reissner Nordstr, or you may have something sort of space-like, but you also always have something like. Okay. So now, I started all this by saying that I want to say this is unstable, right? I want to say also that for some perturbation, let's say of Reissner Nordstr, it should be the case that there's some instability of the Cauchy horizon. So this is a recent result joined with Sungjin Oh, which we put on the archive actually last week. So it's a lot of words. Let me try to sort of say what this means. So remember, in the theorem I just showed you for deformism and deformism, it is a statement about all solutions when the charge is non-zero. Okay, so now I want to understand what happens for blow-up for generic solutions. And of course, I do need to talk about genericity in order to hope that something blows up, because of course there is Reissner Nordstr, which everything is smooth. So I want to say that I can find a generic subclass of initial data in my setting, such that it is the case that if I look at the solution, that is to say the maximal global hyperbolic future development, it is not extendable in an appropriate sense. And what we're able to show is that you can find a generic subset of spherical symmetric data, such that the solution is C2 future inextendable. So even though for generic things you are C0 future extendable, you have a Cauchy horizon, nonetheless the Cauchy horizon is actually singular. The Cauchy horizon is what sort of in the literature it's called weak null singularity. So then, so that's the subset we managed to find, and we want to say also that this subset is generic. So what does it mean sort of for a set of data to be generic? Of course, from the point of view of, let's say, classical dynamical systems, you want to say that the set is open and dense. But of course now I'm working sort of with function spaces. So they're in equivalent ways of talking about topologies of functions. So one has to be very careful, but what we can show is that we can find a set which is open with respect to a weighted C1 topology. So if you have something that's in this set, if you are close to that something in the first derivative, then you are still in that set. Okay, then the solution will still be C2 future inextendable. But I also want to say that, it really is a lot of things. So now suppose you give me something that's not in that. Okay, suppose you give me something that I would call non-generic. Now what happens is that you can find a one-parameter family of data. So you give me this. So I find a one-parameter family, so parameterized by, say, epsilon. When epsilon is 0, is is what you give me. But when epsilon is not 0, then I will immediately be in the generic set. Okay. So then, moreover, is such that at epsilon goes to 0, I approach the given data in any ck norm, whatever k. Okay. So the density argument you can talk about in a much much rougher, much finer topology.
Can you explain what the physical significance of the topology is? So, I mean, when you have metrics that are in the same open set, what does that mean physically?
Right. So I mean, it's just that this problem. Of course, I can also restate my statement that say G is both open and dense in C2 topology. Okay, that's a consequence. But I'm just saying that they're in equivalent ways. So I want the statement that openness is in the strongest sense of openness, and density is also in the strongest sense of density. Because of course, if something is dense in this sense,
No, I don't think you understand my question. I want to know what the topology means physically. You tell me what the open sets are. Great. I want to know what physically these metrics have in common that makes them be in the same open set.
Right. So this is just talking about how I measure. So if you give me two things, I want to say if one thing is in the generic set, then everything close to it is in the
Close in
generic
what
set.
sense?
That's what I'm telling you. Okay. So then what this topology is telling you how to measure the distance, and the distance is measured in the sense of the first derivative of the scalar field.
Okay.
So if you look at you have a coordinate system, you look at the difference, it is small with the first derivative of the scalar field. Please.
So spherically symmetric is still non-generic.
Spherical symmetric is still not generic.
So do you have a sense of what to expect when you go to the non-spherically symmetric?
Yeah, okay. Yeah, wait.
Okay.
Sorry, I'm going too far. So let me just quickly tell you, unfortunately I won't be able to tell you so much about the proof, but I sort of want to tell you sort of a couple of lessons that one can learn from this proof before we actually head to the non-strictly symmetric one. So the first lesson is the lesson actually that we were taught by sort of deformed and Wozniacki, is that you really can, this problem that, okay, ultimately of course you want to say somehow there's something singular, you want to say Cauchy arises instability as was suggested, but you can try to understand stability in the sense of deformed Wozniacki completely independently of trying to understand singular. You don't have to, even if you don't understand that, you can understand that things can be C0 extendable. The second lesson that sort of one can learn is that, the proof, how do we prove this? Actually, by improving this theorem, we need to tell you what the generic set is. So in sort of constructing this generic set, we actually construct a functional, which you should roughly think, so you give me a solution, I would compute something on each of the null infinities. Okay? And if I compute that, that's not zero, then you can show the Cauchy arises singular, and therefore you can extend it C2. So in particular, however you want to think of it, there's something sort of a null infinity that you can compute so that you know what happens in the inside of the black hole. Another thing is that somehow in trying to understand this, what I want to understand, of course, inside the black hole whether things are singular, and turns out this has a lot to do with trying to understand the decay rate of the scalar field in the exterior region. For those who know, I mean, this is related, of course, to the heuristics of price and all that. So one has to understand that. So in order to understand, just generically a singular in the interior, we also establish as a consequence that generically you have a lower bound in the exterior consistent with price's expectation. So now you should really think the proof tells us why you have this blow up. Of course, classically, when Penrose made this conjecture, he suggested that it's because of the blue shift effect in the black hole interior. But it's really a combination of many things, as one can see in the proof. You also need to, it also has something to do with backscattering of waves near the asymptotically flat end. It has something to do with the global geometry of the space-time. Let me not get into that too much, how they relate. But the main point is, once you consider things, the setting is slightly different, you may expect something different. So for instance, if you consider the case in positive cosmological constant, or if you consider extremal black holes, where the global geometry is different, then in fact there are reasons to expect the singularity inside is actually the same.
What about naked singularity solutions?
Right. So of course one also wants to understand this. So somehow in our theorem, we don't consider them by
Because
cheating.
you have a horizon.
Yeah. So there's a theorem one can prove actually it's not too difficult. Is that if you start with appropriate data with two ends, then you don't have naked singularity. So of course, ultimately, you want to understand this problem with one-ended data in the program model, and there, of course, one also has to deal with naked singularity. So, but we want to focus on this issue of the So then we look at two-ended data, and this, I mean, it's actually easy in this setting. I mean, that's nothing. Okay. So, okay, so let me skip this. So of course, you complain, well, strictly symmetric, well, whatever you say about generic strictly symmetric solutions, they are not generic, because, well, they are strictly symmetric. So ultimately, you want to understand Kerr, because, well, that's how I started, anyways. So let's quickly sort of say what one expects in Kerr without any symmetry assumption. So of course, Kerr is a very complicated object, at least in mathematics. Of course, this statement is always sort of considered to be known in many of the physics literature, that we all know that Kerr is stable. But sort of in a fully nonlinear setting, where you want to understand it from the initial point of view, this is actually not known. So there's no proof that Kerr, even the exterior region, is stable. Of course, this is a very, very active area in mathematics. As you can see from the names, I'm missing out many of the names. Of course, Professor Yao has also worked on this problem. So I always worry that I miss out some name in this list, so I never put my name in that, so that I feel sad. Okay. Well, anyway, so this is still not known, so it's hard to talk about anything if you don't know even sort of the exterior region is stable. But let's, for now, assume this, since, for instance, many people in physics would believe this. Now you want to understand what happens to Cauchy horizon in the interior. So here's the theorem. The theorem, joined with the firmest, is roughly saying it's the following. So let's assume the exterior is actually stable. So assume whatever you expect from, let's say, Price's law and so on. So assume in the exterior, perturbations of Kerr actually approach Kerr. Now we just look at the inside, and the theorem says if you have characteristic data thought of as horizons that approach Kerr sufficiently fast, then in fact in the interior you are also stable in the continuous sense. Okay, so in particular it's maybe easier to sort of draw the theorem. Suppose you have data which approaches Kerr here and here, then the solutions remain regular everywhere. Here you have Cauchy horizon, metric remains continuous, and therefore solution continuously extendable. Okay, so in particular, if the exterior of Kerr
continuously and uniquely.
Right, sorry. So continuously. So no. So
you still have the freedom with more initial conditions.
Right. So this is this. Okay. Sorry. This is the next. Okay. So continuously, I have a way to extend. But of course, ultimately, I also want to. So sorry, I should have said sort of right. So in particular, what this says, this you should think of as sort of a negative result for cosmic extension, because you have extension. Okay, but of course, what you still hope to say is, well, this is only C0.
Sorry, I have a question. So say I have a Kerr black hole and I have a baseball outside of it, which is just moving off to infinity.
Yeah.
Flying away.
Yeah.
Do you say that approaches Kerr at late times because the baseball is moving her away, or do you say that, well, there's always some point in the metric where the baseball is, and then it's
so one expects
it's not approaching Kerr.
Right. One expects, of course, you would have changed things. I mean, so let's say you have Kerr exterior.
Yeah.
If you do something sort of perturb.
Yeah.
Right. So the expectation is that you will settle down to a potentially different Kerr.
But so the worry is that the baseball, no matter how far away it is seen from the inner Cauchy horizon, right? So
it is seen
that's
from
why
the
I'm asking. So it seems that I'm worried that when you're defining that you get that Cauchy horizon back, whether your definition of stability is including this possibility that there could be stuff very far away from the black hole.
So I'm just saying that because I have finite speed of propagation. So suppose I only need to know is that things settle down to Kerr here, and things settle down to Kerr here. I don't really for the sake of the theorem, I don't care about what exactly happens sort of the baseball here.
Yeah, it goes up to infinity.
I don't care about what happens. I only care about sort of here. It's vacuum and it approaches Kerr, then you have this. So in particular, if
you say even though the baseball could
Yeah.
be there and
Yeah,
you could
exactly.
be sending
Yeah.
signals, right? I mean, because usually what
I
we
mean,
say
it,
about
but
that,
it's all encoded in the data here.
yeah, but,
it's all
but
encoded.
in some usually in some singular way up in the right hand corner, right?
It's I mean yeah. So you want I mean
yeah, I'm worried
yeah.
about what's happening up there, right? 'Cause
Right,
that's
right.
gonna be the source.
So we need to assume sort of some decay. You should think sort of Price law type decay.
Yeah, but doesn't that mean in particular that you don't have stuff that's sort of arbitrarily far away?
No, you do. You can have, right? It's just that I suppose you have waves, sort of even very far away. Sort of at least the works, sort of these works would tell you that they decay.
But there's a blue shift as it goes back.
There is a blue shift. Yeah.
But you say it still decays?
Yeah, but the blue shift sort of secretly you only see here.
Yeah, but isn't that what you care about?
Yeah. But then but of course in the exterior I already said that somehow I assume everything's stable here before the blue shift, because things decay. And even there's a blue shift. Even there's a blue shift, the claim is the blue shift is not sufficiently strong to destroy the existence of a Cauchy horizon. Okay, so that's the thing. Okay, so let me end by saying that but then you would expect indeed there is a blue shift. I'm telling you that things are stable only in a continuous sense. You should think sort of this is a falsification of a very strong formulation of strong cosmic censorship in the C0 sense. But of course, you also wonder, is there actually some instability, like in the strictly symmetric case? So one conjecture, this is indeed the case, that if you look at generic perturbation, I won't have time to explain why I entertain this notion of instability, but then you cannot extend in this particular sense, but this remains to be seen. Okay, sorry I went over too much. Thank you.
So we have time for maybe one or two questions.
Yeah, so something really bothers me, but so this is a more general question about. So I think that Penrose originally formulated cosmic censorship because he thought that general relativity was somehow in trouble if there were singularities that were not inside event horizons. But that view, which is now half a century old, I think is antiquated and wrong, because we expect theories to break down.
Right.
So if there's a singularity, it just means that there's corrections to Einstein's equation. And there's no physical reason that, in fact, it's an annoying thing. We wouldn't need to build the LHC if there were, singularities occurring out there. It isn't a contradiction of anything. It isn't a threat to determinism if we can see regions where general relativity break down.
Wait.
Secondly, it's not true in higher dimensions. And thirdly, in the real quantum world, things evaporate, and black holes evaporate, and we do get regions of Planckian curvature. So I think that the original motivation of cosmic censorship is just wrong, but nevertheless, so I don't think there's a physical reason to think it should be true. It's not like the positive mass conjecture, where general relativity would have been inconsistent if there were not a positive mass conjecture, because the vacuum would be unstable. So I don't think there's a physical reason, yet it seems to be almost true. Is there a mathematical reason for thinking it should be true? Why is it almost true?
So I think there are sort of three questions that have been asked. So the second and third sort of relate to things I don't really know, sort of quantum gravity I had mentioned. So let me just try to respond to the first and try to defend Penrose. So in fact there are in some sense sort of two cosmic censorship conjectures. So usually sort of one known as the weak one known as the strong one. Of course we know that they are not logically related. But the weak cosmic censorship exactly is sort of trying to rule out things that you say was coupling but not, which is you have singularities which are not in the horizon, right? So that's that's what the weak cosmic censorship conjecture says. But the strong cosmic censorship conjecture, in a sense, there's something quite different. Well, you can think of it sort of from the formulation I just gave. It's about extendability. But if you sort of use the language you were just using, what exactly is troubling is not that you have a naked singularity, right? In Kerr, the problem is exactly not that you have a naked singularity. Of course, you can say in whatever analytic extension you do have a naked singularity, but that's not what I care about. I only care about sort of what's determined by data. And the problem is exactly that there's no singularity. So if you want to say, well, because you have a singularity, you should introduce correction, then this will be troubling because there's no singularity. So then I think this is at least the point of view I would say. Right, so this is, I mean, it's very different sort of to think about the strong and the weak cognitive. The strong cognitive censorship tells you, I mean, it's sort of different, right? Weak cognitive censorship tells you that you should not have singularity outside of the horizon. So my strong cognitive censorship wants to tell you that you should have the singularity inside, is what, and it is the later that. I'm not saying that the former is uninteresting, it's also very interesting mathematically, but it's the later that I'm more concerned.
Yeah, I think we're going to have to
Sorry.
end it here, and we can ask Jonathan, or we can talk to Jonathan after the second colloquium. Let's thank him again.
Our second talk will be by Joao Penedones, and it will be a lecture talk, so please make yourself comfortable. Yeah, and he's visiting us from Lausanne, Switzerland, and he will be also giving a talk today at 4:15. Physics department, if you would like to talk to this person, you can maybe take to the other one. And his work is mostly on so-called deformed theory, which played a prominent role in the studies of quantum gravities due to gauge gravity conjecture, and today he will tell us about polarized black holes.
Thank you very much. Let me just write the name of my collaborator. So Lauren Greenspan, she just finished her thesis about this work, so she was the main driver of this work. Okay, thank you very much for the invitation. And so this talk, so I hope you interrupt me with questions because I don't really know exactly what technical level I should aim at. So this talk is kind of structured in the opposite of the usual way. So I will end with the motivation. Because what brought me to this problem is a bit more technical and harder to explain than so that's to the end. And I will just start by explaining this very intuitive and geometric picture of what's a polarized black hole. Okay? Okay. So let's start by that then. So a polarized black hole, so when the idea is just you have some neutral body, okay? So for example, when you have some molecule, for example an N2 molecule on air, right? If you apply an electric field, it will polarize, right? So positive charges will accumulate on this side and negative on this charge on this side, and so you will have some dipole, an electric dipole, which is proportional to the electric field, okay? Let's say to first order for small electric field. If you remember, this is basically the reason why the sky is blue, right? Because when the electric field from the radiation from the sun creates dipoles that oscillate and then they radiate, and this depends on the frequency, and so that's why the sky is blue. So now the question I want to ask is, take some neutral black hole, okay, some Schwarzschild black hole, and let's apply an electric field, an external electric field to it. Okay. What will happen when we do that? So, okay, I think that you should expect that it will also polarize like a molecule, and like the molecule also changes slightly its shape because the charge is all pulled apart. Here we will see that the black hole also gets deformed. So under the presence of the electric field, the black hole will somehow get some kind of peanut shape form. Okay, so that's the intuition for what I was saying. Any questions?
Where's the charge currents come from?
Yeah, exactly.
So when I say, okay, maybe you can ask again, but when I say I'm applying an electric field, it's clear that this question will make sense if I'm considering Einstein gravity with a Maxwell field, right? So when I say that charges accumulate, I just mean that there will be a flux of electric field coming out on this side and coming in on this side of the horizon. So what actually is charged inside the black hole, I have no idea. Right? I will always talk about stuff outside the horizon.
So does your theory need to have charged matter, or can it just be?
No,
It's backwards.
no, this is without charged
Okay,
matter.
okay. So
It's just the flux of the electric field.
Are you treating the electric field as a test field, not contributing to the metric?
No.
back reaction.
Without back reaction, you would not get
That's right,
deformation.
yeah, okay.
Yeah, so
For your purposes, a charge is just the intersection of the field
it's
line
the
with
flux
horizon.
of the electric field, yeah.
Okay.
So that defines a charge density. Yes. So okay, maybe the words are not, but okay, those are the correct words, right? The flux of the electric field is what I call a charge density. It's Maxwell, one of the Maxwell laws. Okay, so this problem as an exact solution goes back to Ernst, I think, in '77. So okay, this is hopefully the only metric I will write. So let's see. So you start from Schwarzschild. So you have 1 minus, let's say, R0 is the Schwarzschild radius of the horizon. So let me just write Schwarzschild metric. The R squared in 4 dimensions. Okay, the usual Schwarzschild metric. And now what Ernst showed is that there is a very simple deformation that creates this background electric field, which is you just have to group these two things in different forms. So you multiply here by a function, I guess it's lambda square of r and theta, and you divide here by the same function. And this function is very simple. It's just 1 plus, and it's proportional to the electric field. Times theta. I guess it's like quarter here. And so this, the electric field in the background, so I'll just write the potential. The electric field is the gradient of that. It's just E times R minus R0 cosine theta. So this is exactly, so far away, this just gives you a potential which is E times R cosine theta. So I start from a black hole like that. So theta is the usual angle from the North Pole, and the electric field looks like that. And that's an exact solution. Okay?
This is asymptotic to the Melvin.
Exactly. Exactly. So some properties about this solution. So first property is that if you think in terms of just weak applied electric field, okay, so let's just work at first order in E. You see, back reaction is of course quadratic in E, so there's no back reaction at all. And another thing you can see is that there is no electric dipole. Okay? So dipole, the electric dipole is actually 0 to first order in E. Okay, so that's a difference from the molecules. Okay? So it's, although you're applying an electric field, the black hole doesn't create a dipole to first order. So the second.
Why are you just saying it looks like it's just linear in E? So why aren't you just saying it doesn't create a dipole?
Because a dipole, right? A dipole. It would be you would have cosine theta, and the dipole would be a term here proportional to. So you would have r from the background field, and then you would have a 1 over r square, right? That's the solution asymptotically.
But we could change coordinates, we could find that's not.
No, but asymptotically these are the right coordinates, right? If E square is 0 to first order, it's asymptotically flat.
No, it says asymptotic.
No, if
if E squared.
If E squared is 0, right? So this is just asymptotically flat. So you are in flat space-time, just analyzing Maxwell equations, and to read off the dipole, you just go to the potential and you see the term of order 1 over r squared times cosine theta. And there's no dipole.
Why do you say there is a dipole to higher orders? That's what I'm confused. Oh, because you say
No,
you
that part I'm not saying.
Oh, okay.
I'm not saying. Because, but that part is hard, because to higher orders, space is not asymptotically flat, so it's not clear what you mean. So that's, I'm not saying anything about higher order. So, but, so that's the second point, which is it's not asymptotically flat. So that's an important, and the issue comes, you can see it right away here, right? So when R is very large, this term kicks in, so this is much bigger than 1. So when R is much bigger than this 1 over E, so actually the circles, if you take, for example, take θ equals pi, the circles along the equator, instead of growing with R, the perimeter instead of growing with R starts to shrink. So this space is completely different from flat space.
There is a constant energy density of the electric sphere, so it's,
Exactly.
it's just like the universe field with
So it completely changes it. It destroys infinity.
Yeah, that was what I was confused about.
Sorry, one person at a time.
If it kind of collapses back in, it's, I mean, it's
Yeah,
opposite.
so if-
Systems that have a collision with the field lines, so they end at infinity.
So the field lines, so what I'm saying is that now phi, take θ equals pi over 2, so take some equator here, and measure this length, okay, as a function of R, and this length decreases when R goes to infinity. So first it grows, but then it decreases. But the field lines are like that, so the solution is consistent, it's just that asymptotically is completely different from flat space. Was that another question?
Yeah, I'm sorry, I don't understand. You're saying the electric dipole moment may vanish to all orders in E?
Again, I didn't talk, I only talked about first order. I don't want to make any statement.
But you're saying it
It's
may.
still defined.
I mean,
Like
Then
that
what
expression.
is that picture?
Does that picture make sense?
What does that picture mean?
No, good. So let's discuss this picture. No, this picture makes sense because you can ask the flux of the electric field as a function. So on the horizon, you can measure the flux of the electric field as a function of, so let's say, as a function of θ and phi. Okay, it will not depend on phi, of course, but that's a symmetry as a function of θ. And you will see that it changes sign. It's positive on one side and it's negative on the other. So you will get this induced charge density if you want.
How is that consistent with the dipole moment relation?
Right, because this is a local measure. You measure the distribution like that, but asymptotically, if you just measure if there is a dipole, you don't see it.
But I mean, is it wrong that we think of the field lines as kind of coming out one end and going around and coming in the other end?
They don't do that, right? There's a background electric field. Some field lines just continue,
Yeah, some do that.
and some curve here and come out the other end. Yeah, exactly.
Oh, but you said there are never any that go around and come back. That's kind of.
No, they will, right? Even in the molecule, they will not do that. You have a background electric field. You can, if you
Well,
subtract the
charge.
constant
If I
field,
subtract
you
from
will
it,
Yeah.
then okay.
And you will see.
Yeah, fine.
It's not surprising there is no dipole because we didn't have charges to start with. In the system.
Well, okay, you will see that
You kind of secretly do though.
That's
Yeah.
when the vacuum polarization.
it's really a factor of flat space. So if
That's
I will do the same experiment inside a box, and then there will be a dipole.
The same argument would say there are no charged black holes, so that can't be the right argument.
what?
The same argument you're making would apply to monopole moments as well, which would say there are no charged black holes. That's not true, so that.
Well, if you put charge on the black hole, it will be charged.
Yeah, but you can imagine there are solutions that we call charged black holes of theories that don't have any charge matter.
Because it doesn't matter outside the black hole if there's no charges.
Yeah.
So the norm squared of F doesn't vanish at the horizon?
No.
No, definitely not.
So the potential vanishes, but there is an electric field. And so what about the geometry? So you can also just go to this metric, go to the horizon, set R equal R0, right? So you have some two-dimensional surface, and you can just analyze the geometry of this surface. And you can even plot, so embed this geometry in three-dimensional Euclidean space, and really plot this geometry, and you see this kind of peanut shape. Not exactly like that, it's more extended. But you see exactly that. But the the parameter that controls the amount of deformation is, as you can see here, is how much this factor, electric field times R0, right, is this parameter. And this morning I did an estimate, so there is also a similar metric for magnetic field, okay? So basically we just replace E by D, so there's a magnetized black hole. And you might ask what happens in actual astrophysical objects where you have strong magnetic fields. So I did some estimate this morning, formed some magnetar. Wikipedia told me that there's like 10 to the 10 Tesla. So B would be 10 to the 10 Tesla. So if you rewrite this in actual units, introducing Newton constant and all that, you get R0 over some characteristic length scale that depends on the electric field, some characteristic length scale. Right? This is the actual small parameter, or dimension-wise parameter that controls the deformation. And for this, I get L like 10 to the 9 meters. But these magnetars are only 10, 20 kilometers, I think Wikipedia said. So 10 to the 4 meters, okay? So it's always small, okay? I think astrophysically this effect will always be a tiny information.
You would also have a vacuum breakdown if it involves the electric field strongly. You would create pairs out of the vacuum.
Right.
Which would change everything.
That probably.
It's 10 to the 12 instead of 10 to the 60. Well, it's a few orders of magnitude below that if you have an electric field.
Right, but with magnetic field then
you don't have that creation.
Yes.
Also in the magnetic case, if you introduce rotation, if you look at magnetized curve, the Argo sphere goes to infinity.
If you do what?
If you take that solution, magnetize,
Ah.
and you let the black hole spin, it's really sick. The Argo sphere stretches all the way to infinity. It's not a compact.
You mean with an arbitrary
With rotation?
Infinity is already sick.
Well, no, if the parameter is not negligible.
The divergence is infinite magnetic field? Yes. That's weird.
It's
But
super.
you know what about the English solution is that like infinity, like it's
Well, there's no Argo sphere because
no,
he's
not
impartial, but
function of Argo sphere, like the solution itself.
Okay, let me continue because I will tell. I see I will get to the motivation. Okay, so because of this problem, essentially this problem that the asymptotic. So you see here we wanted to study a strong deformation of the field of the black hole, but to go to that regime you need this parameter to be large, but that means the black hole is already in a completely different space. Okay, so it's like you're not really just studying the effect of the electric field, it's just the original space-time where this object is completely different because even asymptotically it just closes off, it's nothing like flat space, okay? So what I'm going to try to do is to ask the same question inside a box. Okay? So I'm going to consider this black hole in a box. And of course, if you do GR, you know box means anti-de Sitter space. You have a question?
Oh, this way.
So, okay, so anti-de Sitter.
No, you're answering it. That's what I'm saying.
Let me then explain. So what is anti-de Sitter? Just very quickly. So probably I've seen it many times. So it's some space, it's like a box, so there's time, and you can think of it as some kind of spherical box. So T equals constant surface. So take this T equals constant. What is this? This is the interior of a ball. Okay, it's hyperbolic space. So it's the interior of a ball. The boundary is a two-sphere, and there is some. So the constant time surfaces are this ball. Okay. So what I'm going to do, I have this. So okay, it's a box. So it's a very funny box. As you know, it's like the boundary is infinite distance away, but if you send light to the boundary, it will go and reflect and get back to you in finite time. Okay. So it's a box without a center, but it's really a box because the energy is quantized, and you need to put boundary conditions at the wall. Okay? So if you don't know this box, you should think about it because it's really amazing box. Okay, so what I'm going to do is to put. So what can I do now? Now I have a box with a boundary. So now you see it's just electrostatics. I will choose my potential at infinity. Okay, my electrostatic potential at infinity. So I choose on this S2 again the same kind of polar coordinates, the spherical coordinates, and I will just choose an electric field that depends on cosine theta, okay, exactly just at the boundary. Okay. So I will put, let's say, maybe with a minus, so it will be negative on this side and positive on this side. Okay. So what it means is if you have, imagine just pure electrostatics, right? You have a sphere, you put boundary conditions, negative potential, positive potential, you'll just have an electric field going inside, right? It means the solution of Laplace equation inside is some electric field like that. Okay. Here the box is slightly different, there is some geometry, but it's exactly the same type of intuition. So there's an electric field created by this boundary condition. So now, actually, with these boundary conditions, we will have two types of solutions. Okay, one solution is just this empty box with an electric field through it. Okay, so that's one solution. I can call that electric flux. Of course, there will be back reaction. So if I increase a lot this parameter E, there will be a stronger electric field, so it will self-gravitate. Okay, but there exists this solution. But there's also another solution, which is it's a black hole inside. Okay? And of course, the black hole will be polarized. So I can now also put here. First, I start with a neutral black hole, and then I turn on this non-trivial boundary condition, and this black hole will deform. And it will be polarized in the sense that the electric field is coming here and out here. Okay. Okay. And now you have these two solutions that exist for the same type of boundary conditions. So you can do the usual game of black hole thermodynamics and ask which solution dominates depending on the electric field and on the temperature that you put in this system. Okay. So the temperature is also a boundary condition that you put on this sphere. I'm losing you. No questions for
Yes,
Penrose.
but do you
10
just, like,
minutes, 5 minutes.
Do you basically compare the curvature of the surface to the electric flux at any point to get like the picture? Because if you just had a sphere, you'd have the field lines going right through it too. But like to get the higher multiple moments, like is it?
So
how do you like define it exactly? Because it's not exactly.
Well, how do I define this
like
picture?
the dipole. I mean, in some sense, is it based on the fact that the surface is.
So.
Curvature of the surface and there's some flux in it.
So, okay. So there is several things that I can define. So as I said, I can measure the flux of the electric field as a function of the coordinate on the horizon. But that doesn't really give you any particular dipole, just tells you it's like positive on one side and negative on the other. But another thing that you can do is that what you've done at infinity is fix the potential. But you have not fixed the electric field. So you can also measure how the electric field comes out from this side and goes in on this side. So you can also think of that as a charge density on the boundary. And that's actually, in a CFT, that will be exactly the charge density on the boundary conformal field theory. But even if you don't know about CFT, just think about this flux of the electric field. Now the geometry is exactly round because the boundary is controlled by us. It's a boundary condition that we choose on the geometry. And so you can just measure what is the dipole of this spherical distribution of charge. And in this case, it's non-zero. So in ADS, it's not zero.
So you're basically comparing the flux of the horizon to the flux at the boundary, where you know that at the boundary it's creating your uniform electric.
No. So to measure the dipole, I just measure the flux at the boundary.
Okay.
And if E was 0, there's no flux at the boundary, there's no electric field anywhere. As soon as I turn E, there is an electric flux at the boundary with a well, somewhat, not exactly cosine theta, but the first order cosine theta.
But you
That's
dependence.
I'm saying that just as this field just going straight through in flat space, the cosine theta would just be a Z field. So
Yeah.
Yeah.
But that's a dipole.
yeah, well, I mean, no, but but it's just because literally that you can call it every. Yeah.
I didn't understand the problem.
Okay, no, I was just like I think that you're looking at something where like the back reaction causes the field lines to behave differently than if I just like had an electric field that had a sphere.
Yeah,
and
so
then
if
what's
you,
the electric
if you
field
go,
on the sphere
if
as
you
opposed to-
increase E and you do the solution non-linearly, the distribution
Will
is
change.
not precisely cosine theta.
Okay, great. So
But you fix it to whatever you want, right? You just turn on some chemical potential or whatever we want to call
Exactly.
it. Right. And so the boundary condition is fixed, and then you see whatever you get inside.
Yes, exactly. So I only fix this. This was my choice.
Yeah.
Then the rest is response of
Yeah.
the system. Yes. Okay. Okay. So let me just draw here. Here's it as well. So how much time do I have?
5 minutes.
So let me just draw the phase diagram you get. So if you put here temperature and the applied electric field, these are the two parameters you control from the boundary, and then the two solutions they're just determined by the equation of motion. So at 0 electric field, many of you know that there is a phase transition called the Hawking phase transition. Okay, so if the temperature is very low, the dominant solution is just the empty box, just ADS without any black hole. If the temperature is sufficiently high, then the dominant solution is a black hole, a Schwarzschild black hole in ADS. Okay. And now what happens is that this transition between the black hole and well, here with the electric field, you can call it just the electric flux phase, just continues, actually decreases like that. But in this case, so there is no sign that there is some critical electric field or anything. This just seems to continue forever if you just do Einstein-Maxwell theory. Okay? So, yes, that's... okay, any question about this? Maybe I can, in 5 minutes, talk about motivation.
Can you say in some intuitive sense why increasing the electric field makes the black hole win at lower temperature? Somehow the black hole becomes even more entropically favorable or free energy favorable. Is there some picture in terms of why that happens? Why does it go down?
Yeah, I understand.
Oh, yeah.
So I think in terms of the CFT,
Well, we're just involved.
so in terms of the CFT, I have this intuition. So you have some degrees of freedom which are confined at low temperatures, and at high temperatures they deconfine. Now you put an electric field, so that's already like stretching, pulling one charge apart from the other. So then it's less temperature is needed to actually deconfine them. But there should also be just a pure gravitational argument.
But in the book, it's kind of intuitive, right? It's like trying to produce, but not quite. So it lowers its energy by polarizing.
Yeah, somehow it's easier to kind of get back to the black hole.
Yeah.
Because there's already some energy there.
So I'm still confused about the dipole business. So you first took this asymptotically flat black hole, and that guy you said to leading order in E there is no dipole.
Yeah.
You have to go to E squared to see anything.
But to E square,
E squared was modifying the space-time itself. Fine, I got all of that. What is the equivalent statement for this problem? Is there a first-order dipolar distortion?
yes. So here, so I would define the dipole by taking, so take this electric field and compute its flux. So take the normal to the boundary. So take E dot n, okay? And this will be a function of theta always. And so call that rho of theta. charge density is infinity. So the dipole, if you want to do some cosine theta, rho of theta, I guess. Well, with the proper measure, I guess, sine theta. I mean that, I think I mean that. Something like that. Okay, so if
Wait, I'm
But
still lost.
to get the electric field, you needed to have this distribution of charge.
yeah,
When
so
you already
rho,
put your
rho is
constant,
proportional to E cosine theta to first order, okay, with some parameter. I can actually write this alpha, and if you write this integral, this will be proportional to, this will be equal to some number alpha E.
So
Isn't
you're
that true?
defining a background constant field as a dipole. And so, I mean, in some sense, normally I would think of like the charge distribution. Like, that's sort of confusion before a little bit.
But okay,
And
maybe-
you're right, it's just a constant field. It's not like you polarize anything. If you had a flat space and you had a constant electric field,
With no
I
black
just
hole.
draw a circle or sphere, I mean, sorry, and I could have
Good,
a
good,
field.
good.
You
Yeah,
know, like
it's
that's
true,
not a
it's
dipole,
true.
right?
But
So
you can, okay, I agree with you,
That's
but for example, you can subtract.
no, yeah.
You could
Yeah, and
compare
then look at
the
differences,
solution
fine.
with black hole and
Yeah,
without black
yeah.
hole and take the difference.
that's-
If you want to
that's
compute
curious
like the
about.
intrinsic dipole
Yeah,
of
sorry,
black hole.
that's what I.
But actually, sure, it was my mistake. I made this comment and I distracted everyone. This is not really the point. It's not
so what is the answer? I'm still not getting.
what's
So
the question?
is there a first order dipole proportional to E?
With this definition, yes.
No, but
And what is
differing
this
from the
definition?
provide value.
What?
So you're comparing with and without the black hole, and you're saying there is a difference. That's what you're saying. Okay,
Yeah.
that's what he's trying to say.
Okay.
Okay. Okay, now I have 1 minute. Okay, so
I feel like that.
okay, so there was actually a different type of motivation I wanted to tell, but in 3 minutes I have to improvise a bit. So let's use exactly this setup. So in the gauge gravity duality, it tells you that this gravitational system, okay, so this gravity theory that I'm describing here, or a close cousin of that actually, it's equivalent, or it's related. Let me first start like that. String theory, so that my friends are happy, and some conformal field theory in 3 dimensions. Okay. And now this conformal field theory has many parameters. In particular, if you take some strong coupling and some large number of degrees of freedom limit, it will be described. So when there's some limit, like I'll just write n to infinity, this will become this gravity theory, and this will, what is some strongly coupled theory, conformal field theory, on this sphere times r, okay, so times time. So only lives, so there is a theory on this boundary, which is just a field theory without gravity, which is equivalent to this gravitational theory, okay? And so you can also do this calculation of what happens when you apply a magnetic field, an electric field, to just a sphere. Now it's without anything inside, okay? So it's an empty interior, and there is some degrees of freedom here on the surface, and you apply this potential, okay? So this electrostatic potential to be minus z cosine theta. So you will see that charges that live on the surface, positive charges want to go to the minimum of the potential, negative charge wants to go to the maximum, and so it will also polarize. You can do this calculation, and you can also compute the phase diagram. Okay, so you can compute this phase diagram, and actually you get something different. You get something like that. So when the theory is weakly coupled, okay, you get something like that. So this is E, and this is temperature, and this is these are 2 phases that correspond to black hole and non-black hole. I will not go into details there. But the main point is that there is a critical electric field here that you cannot go past that. So what happens if you put this electric field bigger than that? It's that the ground state is no longer bounded from below. Just by putting more charged particles, you just can decrease the energy wherever. So this is in contradiction in this picture, that here you can do it all the way. Okay?
So that's because you don't have charged particles there. And here you can pre-produce and screen the electric field.
That's true, that could be one possibility, but actually, if you actually go through the map carefully, the dual of this theory is not just pure Einstein-Maxwell. You have to have also, on this side, the gravitational theory has the metric as degrees of freedom, AU, and there's also scalar field which is not charged.
But there's also an S5, right? There's another sphere, and isn't there a Gregory-Laflamme instability on that when you get close to the Hawking-Page phase transition?
Here, so here actually it's not usual. It's 33, so it's
I understand it, but there's a Gregory-Laflamme instability on the 5 sphere.
There is no 5 sphere.
There's a 7 sphere.
This is A is 3 times S3 times
excuse me, but isn't there Gregory-Laflamme instability?
Here, but here you can just reduce to that and.
Oh yeah, sorry, it is one of the 7. Yeah, that's right.
You don't even. Sorry, I mean there's a truncation from that higher dimensional supergravity, which describes the fields that are needed here, which is just 4-dimensional.
But that truncation might not be consistent if there's an instability.
No, it's not perfectly consistent. There's some dilaton phi.
But you're talking about the gauge theory calculation. I mean, the dual of this does not.
Gauge theory calculation.
I mean, the dual of whatever you are doing here is the full flash, I guess, 1 times CP3.
Yes.
And that's what it's asking.
Yeah, so I'm saying that you start from the supergravity of AUS4 cross CP3, and there's a truncation that only cares about the fields that I'm turning on, that only has these 3 fields.
So there's not actually a tension yet, right? Because you did that calculation of weak coupling. So
Exactly.
presumably the claim is that at strong coupling this thing moves up to infinity. Is that right?
But actually, what we observe when you compute black holes in this different theory is that it's not true. It's like that. So there is no this flux, electric flux has a maximum value because of this scalar field.
Because of the delta. Oh, okay.
Yeah. So for example, if you plot, I don't know, if you plot, for example, this as a function of E, if you plot this total row, I don't know, or alpha of row, the total charge on the positive hemisphere, it will grow, but then there is some kind of branch like that, so you cannot cross. There's 2 solutions here, and you cannot cross this E star.
Joao, can you wrap it up?
Yes, I can answer. So that's a similar result. Okay, there's actually some region of metastability, but it's not anything. So actually there was a motivation that led us to that was a much simpler, a different setup of the gauge gravity duality, but the message is the same. So the point of this was that try to find a new sharp prediction for the gauge gravity duality that can be tested using this conformal field theory, so this field theory which doesn't have dynamical gravity, but can be, so it's at strong coupling, so it's hard to calculate, but it can be simulated in the computer in Monte Carlo simulations, and in principle, this phase diagram can be reproduced. So this is not the simplest calculation to do, to get a map between gauge gravity duality and CF and an explicitly calculation of strong coupling, but I didn't have time to talk about that. Some other system uses just quantum mechanics, where we also have a prediction, and there's also a generalization of polarized black holes that is important for that calculation. I'm sorry for taking too long.
Well, I think we gave him a really hard time and asked a lot of questions, but maybe there's time for one last question. If anyone has something really burning, they have to get off their chest.
So I was going to ask, because of regardless of this dilaton field, there's also going to be effectively a weak gravity conjecture of the charged particle that will screen the electric field, presumably. Does that?
Sure. So.
But that should play a role in some regime.
So yeah. So what you're asking is that can I trust this solution? Like there are charged fields that exist that I'm just setting to 0. So if I really analyze these charged fields, will they actually be stable in this background or not, right? That's your question. Yeah, I don't know the answer to this question. We analyze some probe fields, but to actually know exactly what is the the action of these charged fields in this compactification is not trivial. So I don't know. We didn't do a systematic study of that yet.
On that unresolved dissonance, let us thank you.
Yeah, so you can take Kerr, and you can add a strong that parameter has to be
I like very much the
I would like to just